functions. Now, power functions technically is anything that says anything like x to the p where x is, or where, p is some power, right? Some real number. Technically, a power function is the thing is okay. Now we're back. Technically, a power function is anything like that, but we've already talked about a lot of those possibilities, right? We've already talked about what to do if it's uh, a natural number, like a positive whole number, like that, right? X squared, well, it's really a polynomial, right? X cubed, x to the 17th, like these are all polynomials. These are things that we know how to deal with already. We've also already talked about how to deal with things like x to the negative 2, because that just means the same thing as 1 over x squared, right? So in the case of a whole number exponent, we already know what to do. It's not really a new thing. It's just polynomials and rational functions. That's why this lands where it does, because we've already talked about those possibilities. Which means really what we're going to be looking at are the cases where this is, so what's new is where p is some rational number. Is it going to keep doing that? Because, okay. Rational, okay. Maybe if I just don't move. Okay. People watching the recording, they're going to be very confused. The projector's freaking out. It's not my fault. Oh, goodness gracious. Okay. One moment, everyone. Talk amongst yourselves. We'll try it the other way. Okay, we'll see if this works. Okay, so what's new is when p is some rational number. Rational number we know really means fraction, right? So what we need to be able to deal with then are exponents that are fractions, like these. This was kind of the theme of the intro video for this week. So let's take, shouldn't take more than 5 minutes or so. Take these things. They're either written with a rational exponent like this, like 27 to the 2/3, that's a power that is a fraction, or some of them are written with radicals, but rewrite each of these the other way. So like I said, we'll take a few minutes to do that. Y'all, talk through it, work together, and then we'll compare notes. Yep. Oh yeah, and if you weren't here Friday or need a copy of the notes, I got some extras up here. All right, how do you read a 2/3 power? Okay, it's two things, a square, right? That's the 2, and a cube root. It's the 3, right? So a 2/3 power or any kind of fractional or rational power, the numerator, like it always does for a fraction, tells you like how many copies. Well, in an exponent, that means, write that many copies and multiply them together. The denominator tells you, like last week talking about fractions, we talked about, how many pieces you're cutting the pie into or whatever. For a exponent or an exponent, that means breaking the base, the whatever this is, up into that many equal pieces, right? Well, that's a root. In this case, a cube root, which means, take the thing and break it up into 3 equal pieces. So this is the cube root of 27 squared, or the cube root of 27 squared. Like you can think of it either way. So to write a cube root, you use a radical and put a little 3 out in front there. That's called the index. Again, you can do those in either order, but I know what the cube root of 27 is, and I don't know what 27 squared is, so I'm going to do it this way. What's the cube root of 27? 3. And what's 3 squared? So that's 9 then. Now, of course, this is a number, right? You could just type this into a calculator directly. You might need to, throw like parentheses around the exponent, maybe, depending on how your calculator does stuff. But you can just type that in directly. But this is how it works. Again, numerator is like a normal power, right? Like a normal exponent. This many copies of the thing multiplied together. That's why we square, right? It's 2 of the cube root of 27. The denominator is the index of a radical. So that's how you read and interpret a rational exponent. How do I rewrite x to the negative 5 halves then? What does this do? So that's a square root. And this? X to the 5th, yeah. And the negative part? Negative moves it to the, yep. Okay, so tell me what it is then. Square root of what? The 5th. 1 on top because it's the reciprocal, right? Negative means reciprocal. So it's the reciprocal of the square root of x raised to the 5th. Well, so for a square root, the 2, the index is implied. Yeah. So that is an index 2, but for a square root, we leave it off, and it's just understood to, yeah, to confuse students, I assume, is why somebody decided to do that in the first place. I don't know. I wasn't there for that meeting, but yeah. So a square root, we don't write the index, but it's applied to be 2. Okay, cool. All right. Well, now do the rest of those. X squared. Then you could actually take the square root. Since the X squared plus one plus not for that, it would be for the moment, all we're doing is rewriting the expression, right? Just to make sure we got this idea of the how these rational exponents work down. So I don't need to worry about the fact that it's 2x minus 5, some kind of algebraic expression. Probably I'm not going to touch that or do anything to simplify that like we did with, you know, a number here. So I'm just going to kind of ignore what that is. What does a 3/4 power mean? What is it asking us to do? A fourth root cubed. Yeah. So I take this thing, right, 2x minus 5, and what I need to do is cube it and take its fourth root. Now, again, if you wrote it in the other order, that's fine. That's the same thing. I don't know why I don't just write it here. Oh, that's a little tail behind. Or the fourth root of 2x minus 5, all cubed. These things are both, you know, sort of variations on multiplication, cubing and taking a root. So you can do them in either order. They commute, they work the same either way. Sometimes that may be easier than others. Like for example, here, if I'm doing this numerically, I would rather do what I did than this because 27 squared is going to be a big number, and then I got to figure out what its cube root is if I'm going to try to do it by taking the square first and then the cube root, right? You have a calculator, so who cares? But sometimes it may make our lives a little bit easier to do it in one order than the other, but they are the same, right? Whatever this is, it would still be 9. And that's the only difference in these two things. This is saying cube first and then take the root. This is saying take the root first and then cube, right? But again, they get you to the same place. Okay, what about E then, just so that we can kind of stay in the same spot here? Three x plus 2 to the 2/5. Okay, cool. Again, I didn't do anything with the radicand. I just rewrote it. It's the base on the thing, and other than that, I'm not really paying any attention to what it says. Okay, and here the cube root of x plus 1. X plus 1 to the 1/3, right? It's one copy of the cube root. So over 3, but just one of them, so 1/3. And then the last one, x squared plus 1 to the 1/2. Like if this was a 3. If that was a 3, this would be a 3, but nothing else would change. Right. Because the 1/2 is coming from there, from the square root, right? The square root of anything it's a cow. I know it's cow. Would be. I got to draw it again. Dang it. Okay. To the 1. Yeah. This square? Okay. So look at what's actually being squared there, right? It's just here, it's not the whole thing. So the difference would be, or I think the difference in what you're describing would be if it was something like this, where it's the whole thing squared, that would be x plus 1 to the 2/2, but 2/2 reduces to, right? Because what you're doing there is taking the square root of a square. Those are opposite or inverse operations with a little bit of a catch about being careful about stuff, but those would cancel, those would reduce, and you'd end up with just, okay. Okay, and more on that, in a little bit. But sort of the point here of all this stuff is that these are the kinds of things that we're looking at now, or that we're adding into, the conversation of stuff that we can deal with. Because if we want power functions that aren't like things we've already talked about, really we're talking about things that look like this. So typically, when when people talk about power functions in this kind of context, really what we mean is radical or root functions. Our materials book, homework, all that kind of stuff, refer to them as radical functions. Some other places call them root functions. But it's basically a function that somewhere in it has a square root or a cube root or a fifth root or whatever kind of root built in when we start. So like look at where we're going, like example 2 there. There's a function that has a square root in it to begin with, right? A square root of x somewhere. That's the kind of stuff that we're talking about. Okay, so for that function, Right, again, the thing that makes it a radical function is that it has a square root with an x underneath it to begin with, right? Just having a square root somewhere doesn't necessarily matter, because if we had, I don't know, the square root of 2 times x, where, like, just to be clear, like, this is just a coefficient, this is just a number. This thing's just a straight line where the slope happens to be the square root of 2. So, like, this isn't really a radical function. This doesn't really work the same way as something like this, where the variable shows up in the radical. Okay, well, for starters, just some evaluations. So, do those real quick. All right, 3x minus 2. So if you plug in 2, 3 times 2 is 6. 6 minus 2 is 4. So we get the square root of 4, which is 2. Plug in 6. 18 minus 2, 16. Square root of 16 is 4, right? So we get 4. So here, points that the thing passes through. C, 3 times 10, 30 minus 2 is 28. Square root of 28. Not a perfect square, but it is 2 and 14. And 14 is 2's prime, but 14's even. So 2 and 7, which is prime. So got a pair of 2's, which means we can write it as 2 times the square root of 7. Okay, which is 5 something. And then 1, 3 times 1 minus 2 is the square root of 1 is 1. Okay, so there you go. There's 4 points that this thing passes through, most of which have nice coordinates. But if you think about it, a lot of values that you plug in are probably not going to land on nice round numbers. It's because these all end up being perfect squares. Okay. Can we plug anything we want into that function, though? Okay. What's f of negative 5? The square root of negative 17, which is not a real number. The square root of 17 or negative 17. So what I want you to, or what we're sort of building up to see, is that this is not a real number. because it's not a real number, if we're talking about this as a function, that means that the function's not defined there, right? So when we graph things and talk about domain and range and where function exists and all that, we mean the real valued part of it, right? What real numbers can I plug in? Maybe point over here. What real numbers can I plug in and get a real number back, right? Because that's an XY pair that I can go plot in the plane, and there's part of my graph, right? If I try to plug -5 in, that's a real number. Like I can locate that in the XY plane, but I get a complex number back, right? I get back something that's not a real number. That means I can't, go graph that or plot that in the same way. That means that this is not in the domain of F. That says of F, not off of F. There you go. Because this is not a real number. And lots of other things would do the same thing, right? Here's the graph of that function. It's a square root function, right? So it looks like a square root function, right? The square root function by default lived, at 0, 0, kind of tucked into that corner and then kind of moves up and to the right in quadrant 1. 3x minus 2. There's enough stuff going on that the transformations get a little bit tricky, but -2 shifts to the right. The times 3 is a horizontal stretching thing. Those kind of interact in a weird way, but it moves to the right a little bit and the shape's a little different. Right, so here's the sort of default square root function, right? Pew, they're from 0, 0. The one we have is, again, stretched a little bit and moved a little bit. What's the domain going to look like then for this function? Is it everything, or are there places where it doesn't exist? For example, can I plug -5 in? No, right? Okay. It doesn't exist anywhere over here, in fact, or even here, until we get to, well, whatever this point is, and then to the right from there. So the domain's going to look something like, starting point to infinity, right? And what we need to know is where that point is. Well, I could try clicking on it. It's 0.66667, this says. What is it really, though? Anybody see it? It's really 2/3, right? How do we know it's really 2/3? We got numbers. Yes, right. We got numbers. 3x minus 2. Really what we're trying to figure out to find the domain of this thing, it's a square root, right? What kinds of numbers can you take a square root of and, get a real number back? Positive ones. Yeah. 0 is okay too. What kinds of things do you take a square root of and you get non-real numbers back? Negatives. Okay, so because this is a square root, the radicand, that's the math word for the stuff inside, must be non-negative. Got to be positive or else 0, right? 0 is okay, so it can be equal to 0 or positive. Can't take the square root of a negative number. That means we need to avoid the inside, the radicand being negative. So if I take this aside and set it greater than or equal to 0, and then move stuff around, add 2 to both sides, divide by 3, there's your 2/3, right? What that says is that x needs to be greater than or equal to 2/3, or if you're not, crazy about the inequality thing and interpreting it that way, think of it as it tells me that 2/3 is important, and then try something on either side.
Like we plugged -5 in a second ago, and we got the square root of a negative number. That's not a real number. That doesn't work. We also plugged in, a bunch of other stuff, and we got things that did work. What's the domain then? 2/3 to infinity. It's everything greater than or equal to 2/3. So 2/3 to infinity, 2/3 should be a bracket because it's included, because it makes the radicand 0 and the square root of 0 is 0. Here, yes. Here, no, because it depends on what happens in between, right? But the thing to keep in mind, the thing to remember, is that the square root of a negative number is not real. So similar to, the rational stuff that we just finished spending 2 weeks talking about, there you can't divide by 0 because that's undefined. Okay, so figure out where you would and avoid that, right? Here, you can't take the square root of a negative number. So figure out where you would and avoid that, right? That's one way to think about what we're doing. Okay, that's how square roots work. We want to be able to kind of generalize this. Here's the square root of here's the square root of x. That's what that looks like, right? Pew starts at 0. That's why we have to make sure that the stuff inside is non-negative, because any square root function is going to work like this, right? We also, way back a long time ago, and we haven't seen it in a minute, talked about the cube root. That's what a cube root function looks like. What's different? It goes both sides, right? It goes both directions because you're talking about a cube root. So you have an odd number of, pieces, right? Which means negatives are going to behave differently. You can take the cube root of a negative number, whereas you can't with a square root. There's a fourth root. What's it look like? A whole lot like a square root, right? There's a fifth root, which looks a whole lot like, okay, 6, 7, 8. You see what's happening? Okay, what does it depend on then? Whether the index of the root is odd or even. This is a lot like the end behavior thing with polynomials, right? Except that the picture's sideways, and to make things functions, we have to kind of restrict some things. But if the index is even, then we have to do pretty much the same kind of thing that we do for a square root. Because any even index here, the same thing's still true. I can't take an even root of a negative number, because an even root means you're talking about, in this case, 4 pieces of things. If they're all positive, then the outcome is positive. If they're all negative, then the outcome is still positive, right? That's why this doesn't work. For an odd root, the same thing's not true, right? Odd roots are friendlier. They're better behaved. They don't introduce any new stuff into the conversation about the domain. Okay, so here's some functions. We need to find the domain of each. Be sure to pay attention to what kind of root it is. Think about what that means, and then figure out the domain. And this one, 3/2 power. Remember that is a radical still. We just have to think about what kind and how to rewrite it. So what do we need to do here? And just, maybe looking ahead to sort of more general, how we answer the find the domain question. First thing we need to ask ourselves is, what kind of thing is it? Okay, I don't know how to write a question mark anymore. Whatever. Okay. What kind of function is this? The important part for figuring out domain is the square root. What does that tell us? What does that mean for us? Well, if there's a square root, we need to make sure that the stuff underneath is not negative. Okay, so figure out everywhere that the radicand then, 5x plus 3, the stuff inside, is not negative. Okay, so we need to know where 5x plus 3 is not negative, right? In other words, where it's greater than or equal to 0. You can do that directly as an inequality if you want. You can say 5x plus 3 is greater than or equal to 0 and then solve that. If you don't want to do it directly, you could figure out, or as directly maybe, you can figure out where it's equal to 0 and then do the usual inequality thing, right? Take whatever that is and check kind of either side. This is linear, so it's only going to have one 0, right? Which means you need to check, two intervals. If you wanted, you could, because this is linear, you could break down the transformations if you wanted. The issue with that is that some of these might get a little bit complicated. Again, you got this like horizontal stretching thing that kind of interacts with the shift in a weird way. But however we do it, we should figure out that -3/5 is important and that x values to the right of -3/5 are okay, and things to the left of -3/5 are not okay, right? So again, I did that with an inequality because it's a linear inequality. I feel comfortable with that. If you're less comfortable with that, that's fine. Don't do it that way. Here's -3/5. If I take something to the left of that, like -10, I get the square root of a negative number, right? Like -50 or something. That's a problem. If I take something to the right, like 0, I get the square root of 3. That's fine. That means the domain is everything to the right of that, right? It goes that way. So -3/5 to infinity. Okay. Pretty good. Anybody have any questions at the moment? All right. Y'all tell me about B then. What kind of thing is it? Okay. It's got a root, right? That part's important. What kind of root then? Fourth root, 4 is even. I see an even root show up. What do I start thinking about? Making sure the stuff underneath is not negative, right? Because even roots and negative numbers are not real. So 3 minus x needs to be non-negative. And solve that, and we figure out that 3 is important, right? 3 is where it is 0, and x needs to be smaller than 3 in order for that thing to be positive. So what's the domain? Negative infinity to 3. And again, if we want to think about transformation stuff, this negative x is a reflection this way, right? So instead of going, pew off to the right, it goes whoop, or something, and like stops somewhere, right? Comes in from the left. So negative infinity to 3. Yep.
How do we get that?
So if you hit the, okay, I'll get this real quick. If you hit the math button on the left and then scroll down, there's a cube root there. And then right under that, it's like option 5. The X, that's a, type in whatever index you want. Root. Yeah, click on that and then it should give you like a little box to type in the index. The other way to do it, if you, are really like can't remember that, or yours looks different or whatever, the other way to do it would be to put in something like that, right? Or sorry, it's fourth. Yeah, you could do it that way as well. Okay, C. What kind of function is this? There's a 3/2 power, right? If we rewrite that, what would this look like? A square root and a cube. Square root and a cube. Okay. So for the purpose of domain things, let's look at all the individual little pieces. -3 minus x over 2. That's just a linear thing, right? Dividing by 2, adding -3, like add, subtract, multiply, divide. Those are linear operations. Those don't do anything with domain stuff. So the thing underneath is fine. The cube. Well, when you cube things, does that, add stuff to the domain conversation? Not really. I mean, x cubed is a polynomial. Polynomials are nice. They're defined everywhere. They're easy to work with. The part here that we need to be paying attention to then is the square root, right? The square root's the thing that really affects what we're going to do here. It's a square root, meaning it's even. So what we need to figure out then is where the stuff underneath the square root is greater than or equal to 0 again. I'll let you all finish that one. But basically, I get to just ignore the cube because the cubing part isn't going to change anything about how the domain works, right? Much like taking x and dividing it by 2, you can divide positive numbers and negative numbers and 0 and whatever you want by 2, right? And you just get another number back. That doesn't affect what happens with the domain. Neither does adding 3 or subtracting 3. Neither does this. The square root is the thing that is going to sort of control how this thing works. All right, and the last one, what's different? The cube root, which is odd. If x is a real number, is 2x also a real number? If I give you a number, can you multiply it by 2? And you just get another number back? Okay. Can you subtract that from 8 and just get another number back? Okay. So the stuff underneath doesn't really affect anything, right? It's shifts and that kind of thing, but it doesn't change stuff into, being non-real. The cube root. Well, if I take a cube root function that looks like that kind of, right? And apply some shifting and stretching stuff to it, what's the domain going to be? Everything. Yep. And there's not really anything for me to work out there apart from the fact that, noticing that because this is an odd root, that's how it's going to work. Okay. Okay. So that's how domain works for radical functions. Now, there are also, along with that, kind of implications about the range. Maybe just write this on here to kind of reference. The domain is 0 to infinity. The range is also 0 to infinity. So the kinds of numbers that you can take a square root of are things that are not negative, right? 0 and positives. And the kinds of things that you get back when you take a square root as an answer are non-negative as well, right? If you grab your calculator and type in the square root of, I don't know, 36, right? It spits out 6. It tells you the positive or the principal root of that. As long as the thing that you enter, right, the x value you give it is non-negative, it'll give you a non-negative response back. This thing lives only in quadrant 1. This has some implications for how we solve equations. How could we solve this? We have the square root of x to begin with, right? But we want to know what x is. So I think you're on the right track, but maybe think about going the other way. Yeah, to get rid of a square root, the opposite thing would be squaring. If I take a square root and multiply it by itself, the roots cancel because that's, what a square root means, what it does. So that would just be x. If I do something to one side, though, I got to do it to both. Okay, so this says that if x is 9, then the square root of x is 3, right? Okay. And the way we did that was by squaring both sides, applying the opposite, the inverse operation to both sides. All right, don't worry about what's going on over here. Here I've got the square root of x and I want x by itself. To get it out of the radical, I'm going to get rid of the radical. The way to get rid of the radical is to do the opposite thing. The opposite thing, which is squaring. This is a square root, so square. Okay, that's going to be kind of the name of the game. So give these a shot. No, don't try. Do these. Remember my Master Yoda. Okay, so do those for tomorrow, and get into the homework. The homework again is kind of split. There's like two, topics, objectives, whatever. One of them is all about dealing with like domain and the functions themselves and that kind of thing. You should be in pretty good shape to at least get a good start on that. If you have questions, we can talk about them tomorrow. The other ones on solving equations, we'll get into that a lot more tomorrow. So try it if you want, but don't feel bad about holding off on that one for now. All right, y'all have a good day. I'll see you tomorrow.